Okay. Binomial model, is that working out for you guys? Yes.
What chapters will be covered on Fridays?
Up to the stuff I do today. So, I forget, is that 14, 15, 16, or 15?
14 to 18.
14 to 18? So, something like that. So it's pretty much all this probability stuff, okay? Probability, and then today I'm working on sampling distributions, but only the first half of chapter 18. So we're gonna slow things down a little bit, and I think we'll be good.
There's a question where like you have to find the standard deviation of hitting a target or something like that.
Okay.
So why is it the square root of the number of times the number of trials times the probability that you get it times the probability that you don't get it?
Oh, okay. So, it's like a Bernoulli. It's multiple coin flips, right?
Okay.
Okay. And so if you do the probability of, or if you find the variance of one coin flip, it's going to be p times 1 minus p. I don't know if I need to explain that, but it is. Okay? So the variance of one coin flip is p times 1 minus p. And then if you have 10 of those, okay, it's like having, random variable x plus x plus x plus x plus x plus x 10 times. And so the combined variance of 10 of those would be 10 times p times 1 minus p. So that's where you get the n times p times 1 minus p. Or does the book call it q?
Yeah.
Okay. Well, npq or np1 minus p. And then for the standard deviation, we take the square root of that. I can show it up.
Didn't we find the variance before by finding the expected value and then finding the difference between x and expected value?
Yes. Okay, here, let's do this. Okay, so we have this is what we call a Bernoulli trial, which is the coin flip. And we have success, which equals 1 with probability p, okay? And we have failure, which equals 0 with probability 1 minus p. This is our probability table, right? This is okay with everyone. So the expected value, or the mean, would be 1 times p plus 0 times 1 minus p, and so I get the mean to be equal to p. Okay? And then if we want to go for the variance of x, we're going to take each value. So the variance is x minus mu squared times the probability of x. So the first one has a success value, it's 1 minus the mean, which is p. I'm going to square that, and I'm going to multiply it by the probability of that happening, p. Okay? And then I add this thing, which is 0 minus p squared times the probability that that happens, which is 1 minus p. Okay? And so if I do this correctly, plus p squared times 1 minus p, is that right? Okay. Uh-oh. Now we're going to have problems here. Let me factor out a p and a 1 minus p. And what do I have left? Times 1 minus p plus p. Is that right?
Yeah.
Okay. And so this,
0.
this
1.
cancels out to 1. And so I have p times 1 minus p. Okay, so this is the variance of x. Okay, so the variance of x is p times 1 minus p. Okay, is that okay? That's for a single coin flip or Bernoulli trial. So the variance is p times 1 minus p. Okay. Alright, so then if we talk about binomial, in binomial we have n coin flips, or n Bernoulli trials. Okay? So basically, we're just adding up the outcomes of the Bernoulli trials, or the coin flips. So it's like, if I flip it 10 times, the outcome of a binomial will be how many times did it land heads. So I'm just adding up the number of successes. Okay? So this is essentially x1 plus x2 plus x3 all the way up to xn. Okay? And so the mean is going to be n times the mean of x, n times mu. So that becomes n times p. And then the variance, because it's not n times x, but it's x added up n times, the variance is going to be n times the variance of one coin flip. Okay, and so that becomes n times p times 1 minus p. And so when we do the standard deviation, we get the square root of n times p times 1 minus p. And I think the book might abbreviate 1 minus p as q. Okay, but it's the same thing. So this is how we're getting the mean and the variance. Okay. So we learned the rules about the mean and the variance for multiple random variables. And so we have it for one single binomial, one single Bernoulli or coin flip, and then if we do multiple coin flips, as in a binomial, we get this. Okay. Is that okay? So there's a section that I skipped in chapter 17, where it says the normal model to the rescue. Okay, and that section is very closely related to what we're going to cover today in chapter 18, which is on the sampling distribution. So I think I'll just end up covering both of these things together. So let's see here. Okay, so this is just continuing from chapter 17. When the binomial model, if we're doing a whole bunch of coin flips, or a whole bunch of whatever it is, the binomial model ends up looking a lot like the normal model. Okay, so binomial model looks similar to the normal model when n is large. Okay, and n is considered large when n times p is greater than or equal to 10. Just a rule of thumb, but it's a good rule for when we consider n to be large. Okay. And so we can approximate a binomial model using the normal model. So for instance, I could say, we have a special coin lands heads with probability equal to 0.7. I'll say I flip the coin 100 times. what is the probability it lands heads 75 times or more? Alright, if we were to answer this using the binomial, what would we have to do?
100 choose 75.
We would have to do 100 choose 75.7 raised to the 75 times 0.3 raised to the 25. Okay? But it says 75 times or more, so I'd also have to do 100 choose 76.7 to the 76.3 to the 24, plus 100 choose 77, all the way up to 100 choose 100.7 to the 100.3 to the 0. Okay. Are we in agreement here in terms of this is what we would have to do for the binomial? Okay, well, if we want to answer it using binomial, this is what we would have to do. This would be easy to do on the computer, but if you had to do it by hand, it would be incredibly painful and tedious. So, we will use this, this feature to help us out. Okay, so the binomial model looks a lot like the normal model when n is large. Okay, the normal model requires two parameters, or is defined by two parameters. And what are those two parameters? Has a mean and has a standard deviation. Okay, and so the normal model, when we're going to use the normal model to approximate the binomial, we're going to say the mean is equal to n times p, and the standard deviation is the square root of n times p times 1 minus p, or q. Okay? And so I can approximate this question, what's the probability that it lands 75 times or more, with a normal model where the mean is equal to 100 times 0.7, 70, and the standard deviation is equal to the square root of 100 times 0.7 times 0.3, square root of 21, and I don't know what that is, 4 point something something. .58, 583. Okay. All right, and so now I can go for this area. Okay, so what do I do? Is this okay? Or am I losing people anyway? Alright, so I do a z is equal to 75 minus 70 divided by 4.583. And what do I get? 1.09. I look that up. And I can look up the area to the left of negative 1.09 or the area to the left of positive 1.09 and subtract that from 1. Okay, so the area to the left of positive 1.09 is 0.8621. So that means over here I get 1.1379. And so our answer here is about 0.1379. We do run into a little bit of a problem, okay? But it's not that big of a deal, okay? When you do this calculation, the answer is going to be a little bit off because this is an approximation. And the other problem is that the normal model is continuous. So there's no difference when we're asking the normal model, what's the probability that someone is 5 feet or taller, or what's the probability that someone is taller than 5 feet. Those are, they will give you the exact same answer with the normal model because it's continuous. The binomial is not continuous, so there is an actual probability of getting exactly 75 times. And so there is a slight difference between what's the probability of getting 75 times or more versus what's the probability of getting more than 75 times. Okay. However, when we're doing an approximation with the normal model, the question, what's the probability of 75 times or more versus what's the probability of more than 75, will give you the same answer. Okay. Or somebody else might say, it says more than 75, maybe I should go to 76. And then their answer would be different. Okay. And so there's a little bit of, a tiny bit of ambiguity here. Okay. And so people have tried to accommodate this thing with something called the continuity correction. All right. And you can look up the normal continuity correction, but it's not covered in the book, so I feel like maybe it's unfair for me to teach you this thing. So I'm not going to bother teaching you this thing. But I just want you to know, as you're answering these questions, if you experience some ambiguity, okay, and so I'm going to avoid assigning these direct questions here from chapter 17, okay, but as you go through chapter 17, just if you're reviewing this topic or whatever, you might experience some ambiguity. You might say, the question might say, what's the probability of getting more than 75 heads? And you might say, I'm going to go to 76. And the book might say, they start at 75 as the cutoff point, okay? Probably we should go to 75.5. But, so you might experience some ambiguity in terms of plus or minus 1. And that's okay. That's just what happens when you're trying to approximate something that's discrete, where you can either take on 75 heads, 76 heads, or something with something continuous, okay? But not to worry, this is how we can answer it like this. Is this okay? Okay. Well, this feature is nice because we're going to start working in chapter 18 where we're dealing with sampling distributions. Okay? And sampling distributions for a categorical variable is pretty much just like a binomial model. It's very similar. Okay? So chapter 18 is all about sampling distributions. And we're just going to cover the first half of chapter 18, which does sampling distributions for a categorical variable. The second half of chapter 18 does sampling distributions for numeric variables. But we're just going to do sampling distributions for a categorical variable. And this is the idea here, okay? Here we have some population. Maybe the population is all students at UCLA. Or maybe the population is all the people in the United States. Or whatever it is, okay? We're talking about a categorical variable here. So the population is going to be defined by a proportion. There's a proportion P, okay? So maybe we're looking at the population of, maybe our population is all undergraduate students at UCLA. And maybe the proportion that we're interested in, proportion of the population is proportion of transfer students. Does anyone have any idea what the what this proportion is? I have no idea whatsoever. What proportion of UCLA students do you think are of UCLA undergraduates are transfer students?
40%.
Huh?
40%.
40%? That sounds really high.
20.
20. But then, I mean, but nobody in their freshman or sophomore year would be a transfer student, right? Or would they? I feel like transfers are all juniors and seniors. So maybe. Alright, so we can't agree on this, but let's just make up a number. Let's say 18% of all students, of all undergraduate students, are transfer students. We have no idea. I'm just completely making this up. Okay? Proportion of transfer students, or not proportion, proportion that are transfer students, I should say. Or is that the same thing as proportion of? I don't know. Alright, so the proportion that are transfer students, we'll say, is 0.18. Okay? And from this population, we're going to draw out a sample. Okay, so let's say we go, we ask the registrar, so we can get a truly random sample. We say, give me a list of all the students, and I'm just going to randomly select 100 of them. Okay, so I'm taking a random sample of 100 students. Well, what is the proportion of transfer students that I'll see in my sample? So in my sample, if I take 100 students at random, I'm expecting to see something around 18% transfer students in my sample of 100. But because it's a random sample, I might very well see 20% transfer students. I might see 15% transfer students, okay? I could see, you know, a spectrum. I would probably be surprised if 50% of my sample was transfer students, but I would not be really surprised if it was 21, 20%, or 15%, or any type of number that seems reasonably close to 18%. Okay? So, my sample, I would get a sample proportion and that will be, we call that p hat to indicate this is the proportion from a sample and not the population. This could be equal to 0.20. Okay? If I draw another sample of n is equal to 100, my p hat could be 0.15. Okay? And I can keep drawing multiple samples over and over, et cetera, et cetera, et cetera, and each time I would get a new p hat. And the question is, what is the distribution of p hat? Okay, so how often will I see a p hat that's large or small or whatever? Okay, does that question make sense? Okay. So we would expect p hat to be centered around what? Centered around 0.18 p. The population proportion p. We would expect p hat to be centered around there. And what do you think the standard deviation of p hat would be? Alright, so it's a little bit of a tougher question. Okay. But again, here, this is where the normal approximation comes in, okay? Essentially, what's going on here? This is pretty much like a binomial distribution, okay? The population, we're going to assume the population is so large that every time I select a student at random, it's pretty much like flipping a coin, okay? I have an 18% chance that the quote-unquote coin will be a transfer student, okay? So when I'm picking at random, basically each time I'm picking, I have about an 18% chance that the student I pick is going to be a transfer student, okay? We're assuming the population is so large that that applies. And so it's pretty much like flipping a coin 100 times, where the probability that it lands on the transfer side versus the not transfer side is 0.18, okay? And so this is just like a binomial model, except we're not looking at the count of how many times did it land on transfer student, but we're looking at the proportion. And so how do you get a proportion? You just take the count and you divide by n, okay? So instead of saying I got a sample with 18 transfer students, I'm doing 18 divided by 100 and I'm getting, or 20 divided by 100 and I'm getting 0.20, or 15 divided by 100 and I'm getting 0.15. Is that okay? So essentially, all I'm going to do is divide the variance of a binomial by n squared, okay? Because essentially I'm looking at a binomial variable divided by n. And so when we look at the variance, it becomes the variance divided by n squared. So variance of binomial is equal to n times p times q. And essentially I'm going to just take this and divide by n, so the variance of this thing, of our sampling distribution, will be p times q over n. So because we're dividing by n squared. So the variance of the sampling distribution is this, and the standard deviation will then be the square root of p times q over n. So this becomes over n squared. Alright. Don't worry about the derivation, just know this was the key part, alright? But if you're curious how we got there, that's how we did it. Okay. So then I could say, oops. If I'm taking a random sample of 100 students, where the population is 18% transfer student, what's the probability that my random sample of 100 students ends up being 20% or more transfer students? Okay. So we will say the population is 0.18 transfer students. I take a random sample of 100 students. What is the probability that the random sample has 20% or more transfer students? Okay. So again, this is not a question about the population, it's a question about a random sample. Alright? And so we're talking about the distribution of p hat. P hat comes from a normal distribution. And the mean is going to be p, and the standard deviation is going to be the square root of p times q over n, or p times 1 minus p over n. This is just what we've gone over. This multiply out to. Is this okay? So over here, normal model, we're centered at 0.18. I'm going to draw a cutoff line at 0.20, and I want to know what's the probability of getting 20% or more. And so my z-score is going to be 0.20 minus 0.18 divided by the standard deviation of 0.03. 84. And I get a z-score of 0.52. I look up 0.52 and I get 0.6985 over here, which means I have 0.3015 on that side. So my answer here is 0.3015. Okay. So if the population is 18% transfer students, and I'm taking a random sample of 100 students, that random sample could end up being 20% or more transfer students just by random chance. And how often do we expect that to happen? That happens about 30% of the time. Okay. All right. So let's try this. Okay. So I'm going to change the question up on you, and I'm going to say, all right. Instead of taking 100 random students, we're going to take a random sample of 400 students. Okay. Alright, so take a minute or two, see if you can answer this question now. Right. So the population is still 18% transfer students, and we're going to take a random sample of 400 students. What's the probability that the random sample has 20% or more transfer students? So the only difference here is that I'm taking a larger sample. How are you guys doing? Good? Okay, so let's see what happens here. So the population, still 18% transfer students. So when we look at the sampling distribution of p hat, so again, p hat is each sample has a proportion. What's the probability that the sample proportion is 20% or more? The p hat comes from a normal distribution where the mean is going to be 0.18 and the standard deviation is going to be the square root of 0.18 times 0.82 over 400. So I have 0.18 and I get the standard deviation to be 0.0192, I believe. So I find a z-score and I'm going to do 20% minus 18% divided by 0.0192 and I get a z-score of 1.04. So, go to the normal model table, 0.18, 0.20, and I look up 1.04, and the area to the left of 1.04 is 0.8508. So that leaves the area to the right to be 0.1492, and that is my answer. What's the probability that a random sample has 20% or more transfer students? About 15%. About 15% of random samples will have 20% or more transfer students. Okay, if I take a random sample of size 400. Okay. Alright, so this is great and all. Here there's one key assumption here, and that is that the distribution of p hat comes from a normal distribution. Okay? And there's just a few things that you have to make sure to check. Otherwise, this assumption that p hat comes from a normal distribution could be completely wrong. Okay? So before we start saying p hat comes from a normal distribution, there are a few conditions. Conditions must be met. We want to say p hat So, number one, the sample must be selected randomly. And independently. So if you're not taking a random sample, this isn't going to work. Okay, so you must take a random sample one at a time, random independent. That is one condition that needs to be met. This is also probably the hardest condition to actually enforce in real life. Okay, it's just really hard to get a truly random sample. So in real life, we always kind of have to just keep in mind that maybe our sample is not truly random. Okay, but all of our math is kind of based off of this assumption here. Okay, number two, your sample must not be too big, okay? Cannot be too big. And what we mean by that is it should not be more than 10% of the population. And again, the illustration here is that when you first draw a card out of a random deck of cards, or a shuffled deck, you have a 50% chance of selecting a red card or a black card. Okay? So the probability of getting a red card is 0.5 because there's 26 red, 26 black. Okay? But after you draw that first card, technically it's no longer 26 red and 26 black. It could be 25 red and 26 black. And so your probability of getting a red card again is a little bit different. It's no longer 50%. The idea being that if the population is large and the amount you're sampling is less than 10%, the amount that the proportion changes is so small that we can just kind of ignore it and assume that everything continues to still be 18% or whatever p is. Okay? But once you start taking a very large sample, that proportion in the population could actually start shifting a significant amount that we can't ignore it. Okay? So we're just saying if the sample is small, we can ignore any kind of little deviations of p in the population. Okay? But once it gets too big, we can't do that. Alright, and then the last one is that your sample needs to be large enough. It must be big enough so that n times p is greater than or equal to 10, and n times q, or n times 1 minus p, is also bigger than or equal to 10. And so this comes directly from when we were using the normal model to approximate a binomial random variable. Both n times p has to be bigger than 10, and n times q needs to be bigger than 10. So when you do your homework from chapter 18, it's going to ask you to check your conditions and things of that nature. These are the 3 conditions that they're asking you to check. They give names to each of these. Our book gives names to each of these, I should say. Okay, so they call this the randomization condition. They call this one the 10% condition. And this is called the success-failure condition. I've never seen those same names used anywhere else. It's pretty much, but these concepts do apply. Okay, so our book calls it these conditions, but essentially, the sample shouldn't be too big, but it shouldn't be too small, and your sample needs to be selected randomly. Okay. I think that's about it for the normal model. Using the normal model to get sampling distributions for categorical variable. So I did not write a lab this week, okay? But I'm not canceling lab section. I'm going to ask the TA to do some sample problems and review stuff for you guys, okay? So that'll be that. It's just you're going to be sitting in the lab, so there's going to be like a computer screen. You're going to have to look up at the whiteboard that way, okay? All right, so we'll see you guys on Wednesday.